In the Northwest Territories of Canada, a lone geologist labours away with hammer and chisel, struggling to extract a sample of rock from a smooth, unyielding surface. It's late in the afternoon, but she doesn't need to worry about night falling. In the summer field season, the sun is never far from the horizon, and a pinkish twilight reigns. Fieldwork in this corner of the globe is a unique challenge. There are no roads out here, no cafes or hotels, no help if anything goes wrong. This is the land of lakes and bears, and the geologists are far from home. They travelled to this spot first by float plane and then on foot, navigating with one eye on the treacherous, swampy ground, and the other continually on the GPS. It would be all too easy to lose your way out here. The spot they are aiming for looks much like any other in this wilderness, but the geologists' maps reveal what the eye cannot: the nature of the rocks beneath their feet. The geologist's task is to map the changes and figure out the processes that shaped this remote corner of the globe. This is the Canadian Shield, a fragment of ancient continental crust. Finally, on the shores of a shallow lake, they stop. To the south, stands of trees of the Canadian boreal forest march into the distance, but to the north, the Arctic tundra is host to lower, more hardy vegetation. This whole area lies under many feet of snow and ice in the winter. Now the ice is gone, but the geologists still struggle to find the rock beneath multicoloured lichen, which covers every surface in a thick, durable crust. Only where fires have swept through or frost has shattered the surface are we able to see through to the ancient rocks themselves. Their surface is smooth, polished as if by some immense giant's whetstone. But this is the handiwork of glaciers passing through, whose incredible force is enough to grind solid rock to powder, and then use that powder to grind the rocks some more. Erosion by ice, water, wind, will be the fate of all rocks eventually. But this outcrop, so far, survives. This is what geologists call a gneiss, a metamorphic rock with an eventful history. One that has borne witness to the convulsions of the earth on a massive scale. Over hundreds of millions of years, as continents collided, the granite was crushed, baked, folded, twisted out of all recognition. When it's finally uplifted and exposed at the surface, the result is this intricately striated rock, which wears the scars of its torment as a badge of identity. Certainly, it's a beautiful rock. It looks like many other gneisses all over the world. Starting out as igneous rock, a granite that froze from magma at the heart of an ancient volcano. But this gneiss, this hard-worn specimen from the far reaches of Canada, is special. It has seen more history than any other rock on Earth. When the geologist returned her precious samples to the lab, when she carefully extracted the most resilient zircons, and when she precisely measured the proportions of decayed and undecayed uranium atoms, she was finally able to figure out its immense age. For this is the Acasta gneiss, and it is 4 billion years old. It is the oldest rock on Earth. In its 4 billion years at the surface of the planet, it's withstood the cataclysmic collisions of immense continents, avoided subduction at plate boundaries, and resisted the relentless onslaught of wind, water, and ice that have been the death of so many younger than itself. So perhaps it's not surprising that rocks like this are incredibly rare. What may be more surprising is that, however hard geologists have searched, they can't find anything older. The Acasta gneiss is old, but it's not as old as the Earth itself. Meteorites tell us that the Earth formed around the Sun 4.54 billion years ago, and yet the oldest rocks are more than 500 million years younger. More than 10% of Earth's history is missing from the record books, and 500 million years is a long time. It's the same amount of time that animals, plants, all multicellular life has been on the planet. So what could be missing from this first huge chunk of Earth's history? What was going on for all that time? More than 500 billion years before the first crystals of the Acasta gneiss took shape, the Earth was born. The newborn sun shone a weak and watery light over its protoplanetary disk, where gravity pulled specks of dust, then tiny pebbles, larger rocks, and eventually huge protoplanets together. Eventually, a single, roughly spherical body took shape about 150 million kilometers from the Sun. Inside this newborn Earth, heavier elements like iron and nickel felt the irresistible tug of gravity and descended deep into the heart of the planet, where temperatures and pressures soared. The Earth differentiated into core and mantle, the surface of the planet exposed to the cold vacuum of space, cooled and solidified into a thin, igneous crust. For a time, everything went well for the nascent Earth, until catastrophe struck. Another protoplanet, Theia, struck. Scientists aren't sure if Theia hit the Earth with just a glancing blow or if it was totaled in a head-on crash. But in either case, this was no ordinary bombardment. With the force of 1 billion trillion tons, Theia plows into the Earth. The intense pressure sees temperatures soar to several thousand degrees Celsius. Solid rock turns first to liquid and then to vapor. Both planets' crusts are stripped away and huge chunks of their mantles are hurled out into space. As the dust settles, this Earth of 4.4 billion years ago would be unrecognizable to a traveler from today. Glowing red from within, the molten mantle oozes through the cracks of black, glassy crust. It's girdled by a thick, tumultuous ring of rock and dust, the disgorged remnants of both victims' mantles, now frozen and locked in orbit around the shattered Earth. But no observer from our world would last long on the planet's surface. Barely any atmosphere remains. Any gases that had clung to the Earth when it first formed would have been blown away by the spectacular force of the collision. The rock ejected from the mantle rains down to the surface as molten droplets, dust, pebbles, and boulders. And the skies light up, both night and day, as the rocks in the encircling ring jostle and collide with one another, like waves on a storm-tossed sea. Night and day themselves come at breakneck speed too. The immense energy impacted by Theia's collision sent our planet reeling, now completing an entire rotation in just 5 hours. Eventually, some semblance of order begins to descend in Earth's skies. Small rocks collide and stick together and attract larger rocks, which themselves have the gravity to attract more of the orbiting debris. Before long, a single body comes to reign, sweeping up the rocks and dust and clearing out Earth's skies. The moon is born. But it's not the moon we recognize today. Early on, it glows dull red as the internal heat from its accretion slowly escapes into space. As it cools, it becomes a relatively featureless ball of grey rock, pockmarked by only a few craters from collisions late on in its formation. Like the Earth, it's spinning rapidly, and this moon looms large in Earth's skies. It's 10 times closer than today, and from the planet's surface appears about 15 times as wide. With an arm outstretched, it would take an entire palm to hide it from view. The Earth now has a satellite weighing 1,000,000 trillion tons, orbiting just 20,000 miles away, and this new neighbour has a profound impact on our world. Theia's impact injected an immense amount of heat into the Earth. The surface itself may drop below 1,000 degrees Celsius, allowing a thin crust to solidify, but throughout the interior, the molten rock is still a roiling ocean. And the new moon, huddled so close to the Earth, can tug on that inner ocean, like it tugs on our surface water oceans today. The immense tidal forces are enough to deform the entire planet, bulging it outwards, cracking and splitting the thin surface crust as the semi-molten rock swells and surges up. As the Earth and Moon rotate around one another, this towering planetary bulge rolls over the planet in an unstoppable wave, splintering the crust with every rotation. Molten lava spills through the cracks to freeze with a glassy lustre and then be broken anew mere hours later. This is New Earth, the Earth of 4.2 billion years ago. If a traveller were to visit, it could easily be described as the very definition of hell itself. Scorching temperatures make life here unbearable. The surface itself is not stable, riven by lava floods and fountains of magma. There is no air. A sickening march of day and night, overseen by the blood-red, featureless face of a malevolent puppeteer. This is the Hadean, the first of Earth's great eons. An age defined by its resemblance to Hades, the underworld of Greek mythology, land of the dead. Truly, nothing can survive on this hostile, hellish planet. But yet, this time will pass. As the Earth and Moon whirl through space, locked in a gravitational dance through the heavens, they trade angular momentum. Slowly, gradually, they begin to slow down. The Earth's spin slows, and days and nights grow longer. The Moon's spin also slows, and the same gravitational forces that racked the Earth now lock the Moon into precise synchrony. The satellite becomes tidally locked, taking exactly the same amount of time to rotate on its axis as it does to orbit the Earth, destined to see only one of its faces from here on out. The Moon begins drifting away from the Earth at a rate of about 4 centimeters a year, and is still doing so today. Back in the Hadean, as the millennia pass, the moon's constant face gradually shrinks from view, and with it, its violent tug on the battered Earth. The tidal wave of molten rock diminishes, and eventually the thickening crust triumphs. The surface of the Earth is stable. For now. But things aren't so placid beneath the surface. All that heat from the planet's initial accretion and from the catastrophe moon-forming impact is still trapped within Earth's mantle. It roils with vast convection currents sending plumes of semi-molten rock thousands of miles upwards from the diabolically hot core. When this material reaches the crust, it punches through, exploiting cracks and weaknesses in the newly formed rock, to unleash great floods of lava that flow like mighty rivers and pool in hellish, burning oceans. These early volcanoes aren't like those of the later classic stratocone variety that blow themselves apart when they erupt. They're great, shallow shields that sprawl across the landscape, like weeping wounds, oozing layer upon layer of sticky, black lava. But it's not just lava that these giant shield volcanoes discharge. As liquid rock pours over the surface, gases are spewing up into the air. Nitrogen, carbon dioxide, sulfur dioxide, and superheated water vapor all separate from the mantle rock and follow the volcano plumbing up and out of the Earth. But they don't have the power to escape the planet's gravity. The gases cling to the surface, building up, mixing together, and creating Earth's first real atmosphere. A blanket of gas that swaddles the planet's surface, finally protecting it from the abyss of space. High in the young atmosphere, temperatures cool enough for water to condense, and the first clouds form. High and low pressure systems develop, and winds blow between them. On the highest peaks, the first rain falls. But this is no summer rainstorm. Hadean rain burns. Chemical reactions in the cloud tops sees carbon dioxide reacting with water to make a potent acid. Acid rain falls, and acid rivers flow, and before long, acid oceans start to pool. Meanwhile, the turbulent mantle convection of the world begins to exert a more profound effect on the Earth's surface. As streams of upwelling mantle can't escape through increasingly thick volcanic crust, they spread out sideways, flowing as vast and unbelievably powerful currents just beneath the young crust. The rock above is torn apart and carried along with it. Where the huge rocky rafts diverge, more lava pours out to fill the space. And where they collide, they're crumpled and folded, uplifted and subducted. Mountain chains buckle upwards, solid rocks splintering and shearing in excruciating slow motion, while magma is injected from below. All this is powered by the irresistible flow of the Earth's interior as plate tectonics begin. Plate tectonics sees the creation of new kinds of rock, those of the igneous variety sitting inside the crust, cooling slowly, eventually forming granites. Acid rivers and rain gradually wear away the mountains even as they are still forming, over time turning them into grains of sand that will one day become sandstone. And deep in the heart of the mountains, the rocks are so crushed and baked that they change their structure and chemistry altogether. They become metamorphic rocks, like gneiss. It was in the heart of one of these first mountains 4 billion years ago that a rock formed that was destined to stand the test of time. While those around it have long since melted, subducted, transformed, and eroded away, the heart of this mountain outlives them all. Today, it sits resolute under a midnight sun, protected as much by its isolation as its mineral durability. It's been transported around the globe, buried deep, exhumed, worn down by glaciers, encrusted by lichen, and attacked by geologists' hammers. But the Acasta gneiss has survived 90% of Earth's history. It's the last remnant of our newly forged planet and a record of the hell that reigned for 500 million years. If only it could tell us what it witnessed for the remaining 4 billion. Next time, we follow the story of our planet during its earliest epochs, looking at how the oceans first formed and how planetary bombardment from the heavens might have changed our world forever. You've been watching the entire history of the Earth. Don't forget to like and subscribe. Tell us what you think in the comments, and we'll see you in the next